All right, last but not least, a third FRQ from the problem set, and it's got a disk with rotational inertia. There's almost always a third problem that's crazy hard, or it's got rotational inertia, or both. In this case, we'll find out how crazy hard it is. Let's get the old timer going here and see what we can do. This problem did have a lower average score of about 5.5, something like that. So we've got a solid uniform disc supported by a vertical stand. The disc is able to rotate with negligible friction about an axis passed through the center of its disc. Okay. The mass and radius of the disc are md and r, respectively. The rotational inertia is 1/2 nr squared. The string has negligible masses draped over the disc and attached to the top point P, so it's tied on there. One end of the string is connected to an unstretched ideal spring constant K. So that means that ideal spring, we can say that the force is equal to Kx, and then the spring potential is 1/2 Kx squared. Just kind of getting my mind wrapped around that. That's when nothing's attached to the other end. Then it says a block of mass MB is attached to the other end of the string, slowly lowered until the spring disk system reaches equilibrium. So it's not bouncing. There's no oscillations in here. In this equilibrium position, the disk has rotated clockwise through a small angle theta. So it's rotated over. Well, I don't know if we're going to need the theta there, but we can remember that the arc length around the outside here, if it rotates some theta, that means the string has moved some distance x. But let's see, give all algebraic answers in terms of those variables right there. So I'll highlight that, remember that. So the block MB mass isn't on that list. Interesting. Let's see. Derive an expression for the for the mass MB of the block. Okay, so in this picture, MB would be the mass of the block. So it's, sorry, that's a highlighter. It's going to have a weight force, MB times G. It's going to have tension force going up, and that's the block. So for it, I can put like a net force equation and say that F tension minus MB times G is equal to 0. It's sitting there. It's in equilibrium. It's just hanging out. It's not accelerating. So we want to get an answer for that in terms of everything else, which means like any good old pulley problem, we have to have something for the force on the other side. And the force on the other side is coming from the spring pulling down. So we'll have to say that on this side, there's a net force coming from the spring. So this goes around a pulley, there's a spring. So I'm gonna say for spring, we're gonna have tension up minus the spring force down is equal to 0. And then from there, I think it might just be plugging in and simplifying, maybe, we'll see. I think there's more to it because there's no x. There's no x in this thing, so we'd have to do a substitution, but we'll stop there for that one. At times t equals 0, the string on the right side of the disk is cut and the block falls to the ground. On the circle below, which represents the disk, draw and label forces, not components, that act on the disk immediately after the string is cut. So right after the string is cut, it's rotated, the point P is there. Okay, I was confused why there's a diagonal line there. So we should have the force of gravity acting down on it, and then a normal force going up from the support. I know what you're thinking. I didn't think of that, but yeah, everything's got a force of gravity acting on it. And it still has the string over here that's got a tension force in it, but the string on the other side's gone. So I think that's all that we'd have to put there. Derive an expression for the angular acceleration of the disk immediately after the string is cut. So we've already got this equation up here for what's happening on this side. But they want angular acceleration. And when I think angular acceleration, I think net torque equals I times alpha. And we've got that. They're looking for this. So we'd have to have something for torque. And there's only one force acting on it right now, which is the tension force. So the torque on the system would be the force of the tension times the radius. And then that should be equal to I times alpha. I think. That's a good setup. Yeah, that's a good setup. I think, again, we're going to run into problems of having to do a bunch of substitutions and things, but I think that's a good setup. Remembering if something's going to rotate and angularly accelerate, it's got to have a net torque on it. And in this case, it's we know the I already, and we got a bunch of variables, so we should be able to do that. Oh, look, time ran out. Well, let's go ahead and take a look at D here. And there's an E. Cool. It's like, hey, redo the problem again. But for D, we didn't get to it in 5 minutes, but I was also chit-chatting there. It says at time T1, the disk is rotated and point P is again directly above the axle. Sketch a graph of the magnitude of the angular velocity of the disk as it's doing its thing there from T to T1. At T1, it's back. This is back at the top. I'm gonna scroll up here all the way. That's back at the top. And the spring was unstretched then, so there shouldn't be any more spring force. But it started at rest, so we should have an omega that starts off at nothing and increases, but I think it should like taper off. Oops, taper off. Constant? I think it should be like constant at that point. Like it's doing this. Something like that. It's increasing as it gets faster, but then the string, the string's not stretching as much. And it's something along those lines. And then what do they have here? The disk is adjusted so that it's off center, and they want, I'm not doing that. Not in the time that we have. Let's go through and do some scoring of what we did put down and see if we get anywhere close to the mean value here. What was the mean value for this one? 5.5. Yeah, 5.5. All right, so problem 1, part A, for indicating that the sum of the torques on the disk is 0 is 1 point, or for indicating that the sum of the forces is equal to 0. Oh, okay, that's good. So this one right here, spring and gravitational being, they're just summing all that up together into one big step. They're kind of skipping some of the stuff. So this right here would be worth 1 point. For correctly substituting expressions for the forces, so putting in mg's for that, I guess technically I'd get in some of it, but they're doing the torque version. So for correctly substituting for delta x, so I guess I'd get another point here for that because I did these two forces, so that'd be 1 point. And then correctly substituting for delta x, that'd be solving, but we didn't do that. That's the arc length thing. Replacing delta x with r times theta. B, the free body diagram. Yeah, it looks like they call it F axle. I was calling it normal force. For drawing and labeling a force of tension, that'd be worth 1 point. So 1 point here. I'm going to guess that a lot of students would not think to do these two forces. So let's pretend that we didn't do those. But that would be force due to gravity exerted on the disk, that'd be a point. And then for a correct, I would call it normal force. They're calling it force from the axle. And then there's some other scoring things down here, but I'm guessing most of you would get a point there. You'd say that there's the tension force. C, for indicating that the net torque is due only to the force exerted by the disk from tension. So doing this, that equation, cool. Yeah, we get a point there. Like it. For correctly expressing the torque on the disk as the tension to spring force. So saying spring force at some point would get you a point. But I don't know if we technically got that because I didn't say spring force. Let's go on to D then. D, so we get, that doesn't continue. For a sketch that starts at 0 and monotonically, that is the first time I've ever seen that word, increases until time T1, 1 point. Okay, so I'm going to call that 1 point. I don't know if that's monotonically enough for it, whatever, but sketch is concave down between. Okay, so if you were to do it just as a line, you would not get that last point. Sorry, I'm going to like copy that and look it up here. Like, what the heck is that? monotonic function, non-decreasing function. Okay. All right, back to the problem. So I would give us a point for that. And then part E, didn't even really look at it, and it was worth 3 points. That's not a trivial amount. Okay, so let's see what we would get here. 1, 2, 3, 4, 5. Hey, that's the mean value. I count that as a win on this one. Tricky problem, and you can take a look at the rubric to see what else is going on there. But that concludes this one. Take a look at the solutions.